In this video, I'm going to show you how we can solve second-order homogeneous linear differential equations with constant coefficient. A second-order differential equation is in the form of ay double prime plus by prime plus cy equal 0. Note that we say this differential equation is a homogeneous differential equation because the other side of this equation, here in the right side, we have 0. So a differential equation is homogeneous. A second order differential equation is homogeneous when the other side of the equation is 0. We say this differential equation is with constant coefficients because the coefficient of y double prime, y prime and y, a, b, c, all of these a, b, c are numbers. So because a, b, c are numbers, we say the differential equation is with constant coefficients. And we say this differential is linear because none of y, y prime or y double prime have degree other than 1. The degree of y, the power of y is 1, y prime to the 1 and y double prime to the 1. That's the reason that we say the differential equation is linear. And we say this differential equation is of second order because we have y double prime. If in a differential equation we have y triple prime, we say the differential equation is of third order. And of course, if we have, for example, 5 prime, it is of the fifth order. Of course, we don't show a fifth order differential equation with this form. We show it like this. Instead of putting 5 prime above y, we just put 5 with the bracket as a power of y. And this means that the fifth derivative of y. Anyway, back to our question. How we can solve this type of differential equations? For solving an equation like this, first we have to write the characteristic equation. Characteristic equation is an equation that can help us to solve this differential equation. And the characteristic equation is this equation. AR squared plus BR plus C equal 0. So for writing the characteristic equation, just we need A, B, and C. We put A, B, C, which are numbers, as coefficients here in a quadratic equation. If you notice, a characteristic equation is actually a quadratic equation, a simple quadratic equation. And if we solve and find R from this quadratic equation, easily we can solve the differential equation. When we solve a quadratic equation, three possibilities we have for R. It is possible that when we solve this quadratic equation, we have two different real roots. So two distinct real roots. This is the first possibility. So when we solve this, if we get two different numbers for R, then it is case 1. We have two distinct real roots. And in that case, the solution of this differential equation, y equals to C1, C is a constant here, C sub 1 is a constant, e to the R1 x plus C2 e to the R2 x. Note that in this formula, C1 and C2 are just constants, and R1 and R2 here are the two distinct real roots that we get from solving this quadratic equation. Let me show you an example of this case before we go to the next case. Our first example is y double prime plus 2y prime minus 15y equal 0. The first step for solving second order linear homogeneous differential equations like this is to write the characteristic equation. What is the characteristic equation? R squared plus 2r minus 15 equals 0. Note that here the coefficient of y double prime is 1. So we have 1 r squared plus 2 is br, so 2r plus c, and c here is negative 15, so negative 15 equals 0. So this is the characteristic equation for this differential equation. Now we have to find r from this quadratic formula. For solving this quadratic formula, you can use quadratic formula, or if it is easy for you, you can find r with factoring this quadratic formula. Because factoring this expression is really easy, so it's better to factor this instead of using the quadratic formula. Note that 5 times negative 3 is negative 15, and the sum of 5 and negative 3 is 2. So the factored form of this quadratic equation is this. And from here, if we set this equals 0, r equals negative 5. And from the other bracket, r equals 3. These two numbers are actually r sub 1 and r sub 2. If we plug in these two numbers in this formula, we can find the solution of this differential equation. So y, the solution of the given differential equation, is c sub 1 e to the negative 5x plus c sub 2 e to the 3x. Note that in this solution we cannot find these two constants c sub 1 and c sub 2 because we don't have any initial condition in this question. But if we have initial conditions for this differential equation, for this given differential equation, we can find c sub 1 and c sub 2. But here, because we don't have any initial condition, we leave our answer in this form. And that is the solution of this differential equation. As you can see, solving second order linear homogeneous differential equation is really easy. Just write the characteristic equation, find the roots of that, and then use this formula. 3 simple steps. But the other case that can happen when you want to find r from the quadratic equation is when you don't have two distinct real roots. So this is case 2. So the other case, which we name it here case 2, is when we have repeated root. Suppose when you solve the characteristic equation, instead of two different numbers, you only get one root from solving the equation. Then, in that case, y, the solution of the differential equation, is similar to this, but a bit different. The answer would be c1 e to the rx or r sub 1x plus, but because we don't have any other roots, maybe you think, okay, we can write our answer in this way because the two roots are the same. But no, when a root repeats, instead of writing just similar to this, a term similar to this, you have to multiply your second answer by x. So this is the formula that you have to use when you have repeated roots. The first part is exactly the same as here, but for the second part, because the root is repeated, you have to multiply e to the r1x by an extra x. So this is the formula that you have to use. Let me show you an example of this case. Y double prime minus 6y prime plus 9y equal 0. First, we write the characteristic equation. Again, this is really simple quadratic equation. Simply you can factor this as r minus 3 times r minus 3. Or another way is to use quadratic formula for finding r. It's up to you which method you prefer, which method you are more familiar with. If we set this equal 0, we have r equal 3, and if we set the other bracket equal 0, we get again r equal 3. As you can see, the root 3 is repeated here, so we have repeated roots. And so instead of using this formula, we have to use this formula. If a root repeats, we multiply our first answer by an extra x. So the solution of this differential equation is c sub 1 e to the 3x plus c2x e to the 3x. The only difference between this and this is that here, because the root is repeated, you have to multiply by x. This is the difference between this formula and this formula. But there is a third case, which is a bit more complicated. The third case, so case 3, is when we have two roots, two different roots, but they are complex roots. So instead of having two distinct real roots, we have two distinct complex roots. If you are familiar with complex numbers, you can understand this part better. But if you are not familiar with complex numbers, don't worry at all. You can continue with me and you can understand everything. If when we solve the characteristic equation, we get two complex roots in the form of a plus minus bi, don't worry for a moment if you don't understand completely what this means. But I should mention here that I here in these roots means a square root of negative 1. So anyway, if we solve the quadratic equation, the characteristic equation, and we get two roots in this form, then the solution of the differential equation has a formula that is a bit different with these two formulas. The solution would be e to the ax. A is the number here, is the real part of the complex roots. So e to the ax, a is this number, times by c sub 1, like here, c is 1, c sub 1 is a constant, cosine of bx. B is the imaginary part of the complex roots. Again, I should mention, don't worry if you do not understand everything here at this moment. With one example, everything gets clear for you, I promise you. So this is the solution if we have complex roots. Let me show you an example. Y double prime plus 2y prime plus 5y equal 0. Similar to these two examples, first we write the characteristic equation. R squared plus 2r plus 5 equal 0. If you try to factor this, you will see that it seems it's impossible to factor this. So for finding the roots of this quadratic equation, you have to use the quadratic formula. If you don't remember the quadratic formula, let me remind you the quadratic formula. If we have something like this quadratic formula, a quadratic equation in general, for finding r, we can use this formula, which is famous to quadratic formula. Negative b plus minus s square root of b squared minus 4ac over 2a. This is the quadratic formula. We can use this formula for solving this equation. R equals to negative b. b is 2 here. Note that a is 1, b is 2, and c is 5. Negative b plus minus s square root of b squared is 4 minus 4ac. 4 times 1 is 4 times 5 is 20. So minus 20 all over 2a, which is 2. Note that a here is 1. 4 minus 20 is negative 16. So this equals to negative 2 plus minus root negative 16 over 2. Now note that when we want to take a square root of negative 16, we can write this as root 16 times root negative 1, because if we multiply this by this, we get the same expression. So first we write root negative 16 as root 16 times a square root of negative 1. A square root of 16 is 4. And a square root of negative 1, as I mentioned here, in math, we define a square root of negative 1, I, to be I. So, like, look at this. You are completely familiar with this. A square root of 9 is 3. We have this number in real numbers. But for a square root of negative 1, we don't have any number. In math, we define a square root of negative 1 as I. But if you are not familiar with complex numbers, don't worry. Just memorize in your head. A square root of negative 1 is I. We show it with symbol I. In some textbook, it's not bad to remind you. Some textbook, instead of I, they use J. But the convention is to use I. Okay, so a square root of negative 16 here can be written as 4i. So negative 2 plus minus 4i over 2. Now, notice that if we divide negative 2, if we separate numerator by denominator, if we divide every term in top by 2 by denominator, we can simplify our answer in this form. Negative 2 divided by 2 is negative 1 plus minus 4i divided by 2 is 2. So plus minus 2i. Now if we look at here, a is negative 1 and b is 2. So now at this step, just plug in this number for a in this formula and plug in 2 for b. Then you can write the solution easily. So y, the solution of this second order linear homogeneous differential equation is e to the ax. A is negative 1, so negative x times by c sub 1 cosine of 2x plus c2 sine of 2x. Note that b is 2. And this is the solution of this differential equation. So, even the third case is not really complicated. Just write the characteristic equation, find r from this formula, as we did here, and then use this formula for this case. Now let's do some more examples, all of these cases, to get more familiar with all cases. Let us start with a hard example. Y double prime plus 3y prime plus 4y equals 0. First, we have to write the characteristic equation. The characteristic equation is r to the 2 plus 3r plus 4 equal 0. At first, maybe you try to factor this, but after a few tries, you will see that you cannot factor this. So probably you can guess that the roots of this characteristic equation are complex numbers. So this example should be of case 3. But anyway, always you can use the quadratic formula for finding r. So it doesn't matter if it is case 1, case 2 or case 3. Always use the quadratic formula. It's very simple. Negative b plus minus a square root of b squared minus 4ac over 2a. Negative b, so negative 3 plus minus a square root of b squared is 9 minus 4ac. 4 times 1 is 4 times c is 16. 4 times 1 times 4 is 16. So minus 16 over 2a. A is 1. 2a is 2 times 1, 2. So r equals negative 3 plus minus a square root of 9 minus 16 is negative 7. So r equals to negative 3 plus minus a square root of negative 7 over 2. Because under a square root, we have negative numbers, so this question is of type 3, is case 3. Note that we can write a square root of negative 7 as a square root of 7 times a square root of negative 1. We cannot simplify a square root of 7 because 7 is not a complete square number. So just we have to write a square root of negative 1 here, I. So a square root of negative 7 is a square root of 7 times I. So r equals to negative 3 plus minus a square root of 7 times I over 2. Similar to our previous example, if we separate the terms in numerator by denominator, if we divide everything in numerator by denominator, we can write r as negative 3 over 2 plus minus a square root of 7 over 2 times I. Here, this is a and this is b. And if we use this formula, e to the ax c sub 1 cosine of bx plus c sub 2 sine of bx, y equals to e to the a is negative 3 over 2, negative 3 over 2x times y, c sub 1 cosine of a square root of 7 over 2x plus c sub 2 sine of a square root of 3 over 2, sorry, not 3, 7 over 2x. This is the solution of this differential equation. Let me show you another example. For y double prime plus 4y prime plus y equal 0. The first step again is to write the characteristic equation. This is the characteristic equation of this differential equation. Here you can factor this if you try, or you can use the quadratic formula for finding r. I will show you the both method. First of all, note that we can factor this in this form. 2r plus 1 times 2r plus 1. If you multiply this bracket by this bracket, you can get the same expression. Now from here, r equals to negative 1 over 2. If we set this equals 0, r is negative 1 over 2. And from the other bracket, because it's the same, we get the same number. So this shows that we have repeated roots. And because we have repeated roots, we have to use this formula for the solution. If you remember, the formula was c sub 1 e to the r1x, this number, plus, because it's repeated, we don't have to write the same thing. We have to multiply x here. C sub 2x e to the r1x. This was the formula. And because r is negative 1/2, so the solution is y equals c sub 1 e to the negative 1/2 x plus c sub 2 x e to the negative 1/2 x. Another way that you can find r, if you prefer to use the quadratic formula, you can find r from the quadratic formula. R equals negative 4 plus minus a square root of b squared. 16 minus 4ac is again 16 over 2a, which is 2 times 4, 8. 16 minus 16 is 0, so r equals to negative 4 plus minus 0 over 8. Negative 4 plus 0 over 8 is negative 1/2. Negative 4 minus 0 over 8 is again negative 1/2. As you see, we have repeated roots as here. So it's up to you. You prefer to factor, you prefer to use quadratic formula for this equation. Let me show you another example. 2y prime plus y double prime plus y prime minus 10 equals 0. First, we have to write the characteristic equation for this differential equation. The characteristic equation is 2r squared plus r minus 10 equal 0. Again, if you like, you can use quadratic formula for solving this quadratic equation, or you can simply factor this. It's up to you which method you prefer. If you factor this, you can factor it like this: r minus 2 times 2r plus 5 equal 0. If you multiply this by this, you get the same equation. If we set this bracket equals 0, r equals 2, and if we set the other bracket equals 0, r is negative 5 over 2. If you cannot factor this, if it's not easy for you, always use the quadratic formula. R equals negative b plus minus a square root of b squared 1 minus 4 times 2 times negative 10. 4 times 2 times negative 10 is negative 80. So minus 80 here. All over 2a, 2 times 2 is 4. Finally, r from this equals negative 1 plus minus, this is 81, square root of 81 is 9 over 4. Negative 1 plus 9 over 4 is 2. Negative 1 minus 9 over 4 is negative 10 over 4, which is negative 5 over 2. The same numbers as here. Because here in this question we have two distinct real roots, so we use the formula for case 1. If you don't remember case 1 formula, it was something like this: c1 e to the r1x plus c2 e to the r2x. Note that in this formula, if we have not two roots, three different roots, we can continue this as this. So depending on how many roots you have, because we have here a quadratic formula for quadratic equation, at most we have two roots. But if the equation is of degree 3, then we have 3 roots. If the equation is of degree 4, it's possible that we have 4 different distinct roots. So we can continue this. Here we have 2 distinct roots, so we use these roots in these formulas. So the answer, the solution is c sub 1 e to the 2x plus c sub 2 e to the negative 5 over 2x. Y double prime plus 9y equals 0. Note that in this differential equation we don't have any y prime here. The coefficient of y prime is 0. First we have to write the characteristic equation. A is 1, so we have 1 r squared, but we don't have any y prime, so we don't have any br. Actually we have 0r, which is not necessary to write 0r, plus c. The c value is 9, so r squared plus 9 equals 0 is the characteristic equation of this differential equation. If you try to factor this, actually you can factor r squared plus 9. So for solving this equation, you can use the quadratic formula, or you can find r in this way. You can keep r squared in the left, move 9 into the right, so we have r squared equals negative 9. Now for finding r, take a square root from both sides. R equals plus minus a square root of negative 9. Note that because we have a square root of negative number, it shows that we have complex roots. So from this, r equals plus minus 3i, because a square root of negative 9 is actually a square root of negative 1 times the square root of 9. The square root of 9 is 3, so we have 3 times I. Always we show a square root of negative 1 by I. So r equals plus minus 3i. If you compare this with case 3, which r is a plus minus bi, a here, what is a? A is 0 because we don't have any real part here. So a is 0. So if you like to be more clear for yourself, you can put a 0 here. So don't forget, here for solution, the value for r is 0 plus minus 3i. The other way that you can solve this is to use quadratic formula. Quadratic formula works always. R equals to negative b. We don't have any b here. 0 plus minus a square root of b squared is 0 again. 0 squared is 0 minus 4 times a times c. 4 times 1 is 4 times 9 is 36. Over 2a, which is 2. So this equals 0 plus minus the square root of 36 is 6, so we can write this as 6i. Don't forget we have a negative here, which shows that we have to put I here, over 2. 0 over 2, 0 over 2 is 0, plus minus 6i over 2 is 3i. The same solution. Finally, after we find r, because we have complex roots, the solution is y equals to, if you remember, e to the ax. But what is a here? A is 0. So e to the 0x times by c sub 1 cosine of bx, b is 3, plus c sub 2 sine of bx, b is 3. Because e to the 0 is 1, it's better not to write this and write the answer in this shorter, better form. C sub 1 cosine of 3x, C sub 2 sine of 3x. And this is the end of this video. I hope by watching this video you have learned how to solve second order linear differential equations with constant coefficient. In the next video, I will show you some more examples of these type of differential equations that are a bit more tricky and a bit harder. If you liked this video, please subscribe in my channel.